let's take a look at this survey paper on graph neural networks.
Oh, okay.
It's from Nature Reviews Electrical Engineering.
Hmm.
So it's got to be good stuff, especially since you're an engineer.
Yeah, definitely.
And even if GNNs are new to ya, don't worry at all. Consider this like a deep dive into how they're changing electrical engineering.
And beyond.
And beyond, that's right.
Yeah. And one thing I think is really cool about this paper is it doesn't just talk about like the potential of GNNs.
Yeah.
It really digs into like the real world challenges of actually using them.
Right.
Which I think is really key for anyone who's thinking about applying these things, in their work.
Absolutely. So,
Yeah.
okay. So for anyone who's hearing GNN for the very first time, can you give us like the breakdown? Like, what are they?
Yeah. So basically, imagine you have a network of things.
Okay.
It could be anything like from, components in a circuit to people on social media.
So,
A GNN is basically a type of AI that's built to understand how those things are connected and how those connections affect like the whole system.
so it's not just like looking at one thing on its own. It's
No.
actually figuring out the relationships between them.
Exactly. Yeah. Traditional AI often struggles with that kind of data,
Ah,
but GNNs, they excel at it.
interesting.
And that's why it's so powerful for fields like electrical engineering.
Now, this paper is specifically focused on electrical engineering, right?
That's right.
So what makes GNN such a good fit for that?
Well, so electrical engineering is all about systems, right?
Sure. Circuits, power grids.
Communication networks.
Yep.
And these systems are inherently interconnected.
Yeah.
Just like the graphs that GNNs are designed to analyze.
I see that connection now.
Right.
So instead of using these traditional methods that might oversimplify these systems,
Right.
GNNs can really capture the complexity and give us much more accurate insights.
Yeah, precisely. And, that leads to some pretty exciting applications.
Yeah.
Like you take electronic design, for example.
Yeah, that's a field where even tiny improvements can have huge impact.
Yeah.
Right?
Absolutely. And so GNNs are being used to optimize the design of both digital and analog circuits, leading to faster chips, more efficient power usage, and even the ability to adapt designs for different manufacturing processes.
So they're not just speeding up the design process, they're actually making the circuits themselves better.
Yeah, that's the key. And the paper really highlights how this is being achieved.
Okay.
So for example, in digital circuit design, GNNs can predict timing delays, which is a critical factor in high-speed chips.
Right.
And this is a really complex problem that traditional methods have often struggled with.
Yeah.
But GNNs can learn from data and provide really accurate predictions.
So it sounds like GNNs are bringing some serious brain power to circuit design.
Yeah, for sure.
So what other areas of electrical engineering are seeing this GNN effect?
Another major one is resource allocation in wireless systems.
Right.
So, with the explosion of devices connecting to wireless networks,
Right.
managing bandwidth and power efficiently is a massive challenge.
Yeah, it's like a giant traffic jam of data, everyone trying to connect at once.
Exactly. And so GNNs are being used to kind of direct that traffic, so to speak.
Okay.
They can predict the optimal power level for each device
Right.
to maximize data rates and overall network efficiency.
So instead of like a one-size-fits-all approach, it's more like a personalized plan for each device.
Yeah,
Based on its connections and needs.
that's a great way to put it.
Oh, cool.
Yeah, and that personalized approach is made possible by GNN's ability to understand the relationships between those devices in the network.
Right.
So, they can determine which connections should be active at any given time
Okay.
to avoid interference and ensure reliable communication.
It's like having a super smart air traffic controller for the wireless world,
Right.
making sure everything runs smoothly.
Exactly. And what's really fascinating is that researchers are finding ways to address the challenges that come with applying GNNs to these real-world problems.
Because it's not a perfect system.
Right.
There are going to be limitations.
Exactly. Yeah, and one of the challenges in using GNNs for this, wireless resource allocation is that the network conditions are constantly changing.
Right, because devices are moving around, connecting, disconnecting. The demand for data is fluctuating.
Exactly. So researchers are developing these GNN models that can adapt to these dynamic conditions in real time.
Wow.
They're using techniques like reinforcement learning to train GNNs
Interesting.
that can learn from their interactions with the network and make adjustments on the fly.
So it's not just about creating like a static model.
Right.
It's one that can learn and evolve as the network changes.
Exactly. And this is just one example of the kind of innovative ways that researchers are tackling these challenges of applying GNNs.
Yeah.
The key takeaway, I think, here is that GNNs offer a really powerful framework for solving these complex engineering problems.
Yeah.
But it often requires thinking outside the box and developing new methods to overcome these challenges.
This is all incredibly interesting.
Yeah.
But the paper mentions that GNNs aren't just limited to electrical engineering.
They're making their mark in other scientific domains as well.
That's right. And often it's the expertise from electrical engineers,
Yeah.
Especially in signal processing and system design.
Right.
That helps to push the boundaries of what GNNs can do in these other fields.
So give me an example.
Like particle physics, for example.
Okay. The world of smashing atoms.
Yes.
How do GNNs fit into that?
So the Large Hadron Collider generates this unbelievable amount of data from those particle collisions. And GNNs are helping scientists to sift through all that data to reconstruct particle tracks and identify jets of particles.
So it's like finding a needle in a haystack, but the needle is a tiny particle and the haystack is a mountain of data.
A very chaotic haystack.
Yeah.
But GNNs are uniquely suited to this task because they can analyze the relationships between the particles and identify patterns that would be just impossible to spot with traditional methods.
So they're not just crunching numbers.
Right.
They're actually understanding the interactions between these particles. Yeah.
And kind of piecing together the story of what happened in the collision.
Exactly. And this is another example of how GNNs can be used to solve problems that were previously considered intractable.
It's amazing to see how they're being applied in such diverse fields.
Yeah.
The paper also mentions material science.
Yeah. GNNs are proving to be really valuable in material science as well.
How so?
Well, from predicting the properties of new materials to accelerating molecular dynamic simulations.
Right.
GNNs are becoming like an essential tool for material scientists.
It sounds like GNNs are helping us understand the building blocks of the universe, both at the subatomic level and at the level of materials.
Exactly.
And it all comes back to their ability to analyze those relationships between things, whether they're particles or atoms or devices in a network.
Exactly. And for anyone listening who's thinking, could GNNs be useful in my field?
Right.
I think the answer is probably yes.
Okay.
If your work involves systems networks or any kind of relational data, GNNs have the potential to unlock new insights and solutions.
So even though this paper is focused on electrical engineering, the takeaways here are really relevant for anyone who's working with complex systems, regardless of their field.
Absolutely. The core principles and the methods for addressing challenges and applying GNNs are transferable across disciplines.
This is all so fascinating.
Yeah.
But I'm sure there are challenges too, right?
Of course.
The paper does mention some limitations of GNNs.
Yeah, no technology is without its limitations.
Right.
And one of the biggest challenges with GNNs is data scarcity.
Okay.
GNNs, like a lot of deep learning methods, they thrive on large amounts of data to learn effectively.
Right.
But in many fields, that data is either expensive to collect or it simply isn't available yet.
So even though we have these really powerful GNNs, we need a lot of data to train them properly.
Yeah, that's right.
So what are some ways to overcome that challenge?
That's where the ingenuity of engineers comes in. They're developing techniques like transfer learning, where knowledge gained from one data set can be applied to another, even if those data sets are quite different.
Interesting.
And this is especially relevant for fields where data is scarce or expensive to acquire.
So instead of starting from scratch every time, we can leverage existing knowledge to make the learning process more efficient.
Exactly. It's all about being resourceful and finding creative ways to make the most of the data we have.
This has been an incredibly eye-opening discussion so far.
Yeah.
I'm already starting to see how GNNs could be applied in so many different fields.
It's exciting stuff.
But I'm curious to learn more about the specific challenges and solutions that researchers are working on.
Well, there's a lot more to unpack.
Yeah.
We've only just scratched the surface of what GNNs can do and the challenges they face.
Okay, let's keep digging. Then I'm ready to dive deeper into these specific applications and see how GNNs are being used to tackle these real-world problems.
All right, sounds good. One area where GNNs are really pushing the boundaries is material science. It's a field that's really ripe for disruption, and GNNs are proving to be just the perfect tool for the job.
Yeah, we touched on this briefly before.
Right.
But I'm eager to go deeper.
Yeah.
So what makes GNNs so well suited for material science?
So materials are all about structure, right? Like how atoms are arranged.
Right.
And, the properties of a material, whether its strength or conductivity or even its color. It all stems from how those atoms are connected.
Yeah.
And as you know, GNNs are all about understanding connections.
Right. So it's like looking at a material not just as a collection of atoms,
Right.
but as a network of interactions.
Exactly. And by analyzing those interactions, GNNs can actually predict the properties of a material before it's even synthesized in a lab.
So instead of like the traditional trial and error approach to developing new materials,
Right.
we can use GNNs to design materials with very specific properties in mind.
That's the idea, and it's already happening,
Oh, wow.
Researchers are using GNNs to discover new materials for batteries, solar cells, and even catalysts for chemical reactions.
That's incredible. So it's like having a virtual laboratory where you can experiment with different atomic structures.
Right.
And see how they affect the material's properties.
It's a game changer for material science.
Yeah.
And it's not just about designing new materials.
Okay.
GNNs are also being used to accelerate the process of understanding existing materials.
Okay.
So for example, they can be used to speed up molecular dynamics simulations.
Okay. Can you remind me what those are?
Yeah. So those are the simulations that show how atoms and molecules move and interact over time.
Gotcha.
And they're computationally very expensive,
Right.
often requiring supercomputers to run.
Yeah.
But GNNs can significantly reduce that computational cost, making it possible to run these simulations on much more accessible hardware.
So it's like compressing time,
Yeah.
allowing researchers to study processes that would normally take years or even decades to simulate.
That's a great way to put it. And this has huge implications for fields like drug discovery and materials design,
Right.
where understanding how these molecules interact is absolutely crucial.
It sounds like GNNs are giving scientists a superpower,
Yeah.
allowing them to see and understand the world at a level of detail that was previously unimaginable.
And it's not just about seeing, it's about predicting and controlling.
Okay.
So, for example, in the field of nanoelectronics,
Right.
GNNs are being used to design and optimize the performance of nanoscale devices.
So that's getting down to the level of individual atoms and molecules, right?
Exactly. And at that scale, quantum effects start to dominate. And traditional methods for designing electronic devices, they kind of break down.
Right.
But GNNs can capture those quantum effects and predict how they'll impact the device's behavior.
So they're not just working with the laws of classical physics,
Right.
but with the laws of quantum mechanics as well.
Precisely. And that opens up this whole new world of possibilities for designing electronic devices with unprecedented capabilities.
It's mind-boggling to think about the potential here.
It is.
But I imagine there are challenges too, right?
Of course.
Especially when you're working at such a small scale.
Yeah. One of the biggest challenges is the lack of experimental data at the nanoscale. It's very difficult and expensive to collect data on how individual atoms and molecules behave.
So we're back to that data scarcity problem we talked about earlier.
Right.
So how are researchers addressing that in the context of nanoelectronics?
They're getting creative.
Okay.
One approach is to combine experimental data with theoretical simulations.
Okay.
So GNNs can be trained on data from simulations, which are much easier to generate,
Right.
and then fine-tune on the limited experimental data that is available.
So it's like bootstrapping the learning process by using simulations to fill in the gaps where experimental data is missing.
Exactly. It's a way to leverage the strengths of both approaches. Another challenge in nanoelectronics is the complexity of the GNN models themselves.
Okay.
As we go down to smaller and smaller scales, the number of interactions between atoms and molecules increases exponentially.
So the GNNs need to be more powerful to handle all that complexity.
Exactly. And that requires developing more sophisticated GNN architectures and training algorithms.
Okay.
Researchers are exploring things like hierarchical GNNs, which can learn representations of the system at different levels of detail.
So it's like having different layers of understanding from the individual atoms to the overall behavior of the device.
That's a great analogy.
Okay.
And this hierarchical approach allows the GNN to capture those complex interactions at the nanoscale while still being computationally tractable.
It's amazing to see how researchers are pushing the boundaries of what's possible with GNNs.
Yeah.
But I'm curious about the practical applications.
Yeah.
How are these advancements in nanoelectronics going to impact our lives?
Yeah, it's the exciting part.
Yeah.
These advancements have the potential to revolutionize everything from computing to medicine.
Okay, give me some examples.
Okay, so imagine computers that are thousands of times faster, and more energy efficient than today's computers.
That would be incredible.
What about medicine?
Yeah. How could nanoelectronics impact that field?
So imagine nanoscale sensors that can detect diseases at their earliest stages, or tiny drug delivery systems that can target specific cells in the body.
Okay.
These are just a few of the possibilities that nanoelectronics, powered by GNNs, are opening up.
It sounds like we're on the verge of a technological revolution.
It does.
But it also seems like there's a long way to go before these technologies become a reality.
Of course, there are still many challenges to overcome.
Right.
But the progress that's been made in just the past few years is astonishing.
Yeah.
And with continued collaboration between researchers from different fields.
Right. Electrical engineering, computer science.
Physics, chemistry. I'm confident that we'll see these technologies come to fruition in the not-too-distant future.
It's inspiring to see how all these different disciplines are coming together to solve these grand challenges.
It really is.
It's like a scientific symphony, with each instrument playing its part to create something truly remarkable.
That's a beautiful way to put it, and it really highlights the importance of interdisciplinary collaboration in advancing science and technology.
Well said. This has been an incredible deep dive into the world of GNNs.
It has.
And their applications in material science and nanoelectronics.
Yeah.
I'm starting to see the vast potential of this technology.
Yeah.
And the transformative impact it could have on our world.
It's truly a fascinating field, and I'm really excited to see what the future holds for GNNs.
But before we get too carried away with the future, I'd love to kind of circle back to some of the challenges we've been discussing.
Yeah.
Data scarcity seems to be like a recurring theme.
Right.
Are there other ways that researchers are tackling this problem beyond the techniques that we've already mentioned?
Absolutely. One promising approach is to generate synthetic data using techniques like generative adversarial networks, or GANs.
Okay.
And these are a type of AI that can learn to create realistic data that mimics the properties of real data.
So it's like having a machine that can create its own training data.
It's pretty wild.
That's wild.
And it's a really powerful tool for overcoming this data scarcity.
Right.
Especially in fields where collecting real data is really difficult or expensive.
That makes sense. But I imagine there are challenges with using synthetic data as well.
Of course, one challenge is ensuring that that synthetic data is actually representative of the real world.
Okay.
You know, if the synthetic data is too different from the real data, it can actually harm the performance of the GNN model.
So it's a delicate balance between generating enough data to train the model effectively.
Right.
And ensuring that the data is realistic enough to be useful.
Exactly. And researchers are constantly working on developing better methods for generating and evaluating synthetic data.
It's amazing to see the ingenuity and creativity that researchers are bringing to bear on these challenges.
Yeah.
It really speaks to the excitement and potential of this field.
It is. It's a very dynamic field with new discoveries and advancements happening all the time.
Yeah.
And that's what makes it so exciting to be a part of.
Speaking of excitement,
okay,
the paper also highlights another application of GNNs that I'm particularly fascinated by.
Okay.
Biomedicine.
Yeah.
It seems like a natural fit, given that biological systems are essentially complex networks of interactions.
It is a perfect match.
Yeah.
GNNs are proving to be incredibly valuable in biomedicine.
Right.
From drug discovery to personalized medicine. For example, they're being used to predict drug-target interactions.
Okay.
Which is crucial for developing new therapies.
So instead of the traditional trial and error approach to drug discovery, we can use GNNs to identify potential drug candidates much faster and more efficiently.
Exactly. GNNs can analyze vast data sets of molecular structures and biological pathways to identify promising drug candidates that have been missed by traditional methods.
That's incredible. It's like having a super-powered search engine for drug discovery.
That's a great analogy, and it's not just about finding new drugs.
Okay.
GNNs are also being used to predict how patients will respond to different treatments, paving the way for personalized medicine.
And that's the idea of tailoring treatments to each individual patient based on their unique genetic makeup and medical history.
Precisely.
Okay.
And GNNs can analyze patient data, including genetic information, medical records, and even lifestyle factors to predict which treatments are most likely to be effective for each patient.
That's a huge step towards more effective and personalized healthcare.
It is.
But I imagine there are challenges in applying GNNs to biomedicine as well.
Of course, one of the biggest challenges is the complexity of biological systems. You know, they involve countless interactions between genes, proteins, cells, and organs.
Right.
It's a daunting task to capture all that complexity in a GNN model.
So it's not just about analyzing a single network,
but
a network of networks.
Exactly. And researchers are developing these new GNN architectures and algorithms to address this challenge.
Sure.
They're exploring things like multi-scale GNNs, which can learn representations of the system at different levels of biological organization.
So it's like having different lenses to zoom in and out on the biological system.
Yeah.
From the molecular level to the level of the whole organism.
That's a great way to visualize it.
Okay.
And this multi-scale approach allows the GNN to capture those complex interactions at different levels of biological organization.
It's inspiring to see how GNNs are being used to tackle such complex challenges in biomedicine.
It is.
But I'm also curious about the ethical considerations.
Sure.
We're talking about using patient data to make predictions about their health.
Right.
Are there concerns about privacy and bias in these applications?
Those are absolutely valid concerns.
Yeah.
And researchers are working on developing methods to address them. Okay.
For example, there are techniques like federated learning, which allow GNN models to be trained on data from multiple hospitals or research institutions without ever having to share the raw data itself.
So it's like bringing the learning to the data rather than bringing the data to the learning.
Exactly. And this helps to protect patient privacy.
Okay.
And there are also techniques for mitigating bias in GNN models, ensuring that predictions are fair and equitable for all patients.
It's encouraging to hear that these ethical considerations are being taken seriously.
Yeah.
It seems like there's a real effort to develop GNN applications in a responsible and ethical way.
Absolutely. The responsible development and deployment of GNNs is crucial for ensuring that this technology benefits humanity as a whole.
Well said. This deep dive has been incredibly enlightening.
Yeah, it has.
I'm starting to see GNNs not just as this powerful technology, but as a force for good.
Yeah.
They have the potential to solve some of the world's most pressing challenges.
They do, in areas like healthcare, energy, and material science.
I completely agree, and I believe that the continued collaboration between researchers from different disciplines will be key to unlocking the full potential of GNNs.
This paper has certainly given me a lot to think about.
Yeah, me too.
And I'm sure our listeners feeling the same way.
For sure.
But before we wrap up, there's one more area I'd love to explore. The paper keeps coming back to this idea that electrical engineers really have a super crucial role to play in the advancement of GNNs.
Yeah.
Like, it's not just about developing the algorithms.
Right.
It's also about understanding the underlying hardware and systems that those algorithms will run on.
Yeah, that's a crucial point. The success of GNNs really hinges on having efficient hardware and software architectures that can handle the computational demands of these models.
Yeah.
And electrical engineers are at the forefront of developing those architectures.
So it's like building the right tools for the job.
Exactly.
If we want GNNs to reach their full potential, we need the right hardware to support them.
Right. One of the biggest challenges with GNNs is their computational complexity.
Okay.
They require a lot of processing power,
Yeah.
especially when dealing with large and complex graphs.
And that processing power translates to energy consumption as well, right?
Oh, absolutely.
So making GNNs more efficient isn't just about speed. It's also about sustainability.
Exactly. And electrical engineers are tackling this challenge from multiple angles.
Okay.
So they're developing new hardware architectures like neuromorphic chips,
Okay.
which are inspired by the structure of the human brain.
Wow.
And are much more energy efficient than traditional processors.
So instead of trying to force GNNs to fit on existing hardware, we're designing hardware that's specifically optimized for how GNNs work.
Precisely. And this co-design approach is leading to some really exciting advancements.
Like what?
So, for example, researchers are developing GNN accelerators, which are specialized hardware components that can perform GNN computations much faster and more efficiently than general-purpose processors.
It sounds like we're entering a new era of computing where the hardware and software are evolving together to create systems that are specifically designed for AI applications like GNNs.
That's exactly right. And this convergence of hardware and software is going to be key to unlocking the full potential of GNNs in all the fields we've been discussing.
Well, this deep dive has been incredibly insightful.
It has.
We've covered a lot of ground.
We have.
From the fundamentals of GNNs to their applications in all these diverse fields.
Right.
Electrical engineering, material science, biomedicine, even particle physics.
It's been a fascinating journey, and I hope our listener has gained a deeper appreciation for the transformative power of GNNs.
Yeah.
And the crucial role that electrical engineers are playing in their development and application.
I know I certainly have. This paper has really opened my eyes to the incredible possibilities of GNNs and the challenges that researchers are tackling to make those possibilities a reality.
Absolutely. And I believe that with continued collaboration and innovation, we'll see GNNs revolutionize countless industries and scientific disciplines in the years to come.
Well said. And to our listener, we encourage you to continue exploring the world of GNNs.
Yes.
Who knows, maybe you'll be the one to discover the next groundbreaking application.
Until next time, keep diving deep.